So now we turn on to studying functions, and so this is section 4. We'll start with functional limits, so 4.2, functional limits. So this section allows us to make rigorous the notion of continuity by introducing the notion of limit of a function when x tends to a particular value. This is something that should be very familiar to you, given that you've taken calculus, many courses, and all the calculus sequence, likelihood. And the main thrust now is to revisit these concepts, so to make sure that now we have a solid foundation for tackling problems involving convergence of functions as a number as x approaches a certain number c. And once we have that notion, we can introduce the notion of limit in the same way we did in Calc 1, namely, so if f tends to a particular value L as x approaches c, then the function will be continuous if f is defined at a point and takes on the value of the limit of f at that point. So now, with all the tools that we have, we will be able to show convergence by using or by appealing to previous results, and hopefully that will make things more clear and will give us a sense of that what we're doing is now, doesn't have any holes. Okay, so this is the statement we want to make sense of. So, what does this mean? Okay, so but you probably remember this notation from before, from previous courses. The limit of f of x as x approaches c is equal to L. So there are alternative definitions. There's one definition, the epsilon delta that you saw in Calc 1. There's another one involving sequences whose limit is c, xn goes to c. So if you test all sequences that converge to c, and then the limit of f of xn, which is again a sequence, it's also a sequence, is L, and that happens for every sequence converging to C, then you say the function converges to L as x approaches C. One of the results of this section is in fact that these two things are equivalent, so it doesn't matter which notion we adopt as the definition. But so let's start with the one, the epsilon delta, so the one that is given in the book. So this is the definition. .2.1. It says functional limit. So let f from some subset of R to R be a function, so it's to be well defined. And let C be a limit point of the domain A. We then say that the lim as x approaches C of f of x is equal to L, provided that for all epsilon greater than 0, there exists some delta greater than 0 such that for all x in A, such that the point is not equal to C, and the distance from x to C is less than delta, which this implies that the distance between f of x and L is less than this small number epsilon. It's arbitrarily small number epsilon. Or in other words, so we can phrase this in a more synthetic way. So f of x, so equivalently, I mean, it's just not only equivalent, this is just a rewriting of the same thing. Equivalently, rewrite, I mean, this is different notation, but it's the same. We write f of x tends to L as x approaches C if for all epsilon greater than 0 there is a delta such that for all x A minus C, well, this is actually implied in the next statement, but if you want to add that condition, it's fine. While it's in A, it holds that if this is true, then this is less than epsilon. Okay, so this is the actual mathematical statement of the limit of a function. I mean, the limit. This is the statement that makes us that allows us to make rigorous the notion of the function f tending or going to a particular value as x approaches a certain number c. You will notice here that unlike the definition in Calc 1, this is not an interior point, a is not necessarily an interval, but then it is something we didn't talk about when we studied Calc 1, for instance. There was no notion of limit point, which we introduce here in this course. So C being a limit point is necessary because we want to be able to approach the point C. Actually, C, the set A does not need to be closed. So in particular, C does not need to be an element in A. So this is, if you recall from Calc 1, this corresponds to some situations where you have, say, an open interval and you want to talk about the limit of f of x as x approaches one of the endpoints of this open interval. And so now everything is incorporated in the definition. So the limit, the point c does not need to be an element where f is defined. It's not a problem for the definition. You just want to see what's the trend of f as you approach that number. But in order to be able to approach that number, then c must be a limit point of the domain of f. Otherwise, you cannot really approach that number c. And limit points are exactly that. The points that can be approximated by, such as there's a sequence in the set A that approaches the limit c. Okay, so this is what we need to test. Whenever we want to show that something is continuous, we need to show this statement down here. Okay, so this is the statement that we want to use every time we want to show that the limit of a function is, say, a limit L. This approaches something that, it's a number that is a limit point in the domain of f. A may sometimes not be given to you. Remember that there's some functions that, just like in Calc 1, the domain is implicitly given to you by the fact that the expression that they define makes sense only for certain values and not for others. So for most real numbers, or for at least the positive real numbers, say, makes sense. So those are the things that we need to take into consideration whenever you read a problem. Sometimes the set A may not be given to you, but you have to deduce it from the formula that you're given that defines f. And so now we'll go over a couple of examples to see how we actually show the continuity not continuity, how we find the limit of functions. Then we're going to talk about continuity. These two functions that we're going to cover now, which is essentially the same ones in the book. These functions are continuous. So in order to find the limit or find the candidate for a limit will be very easy. Just plug in the value function at the point C. Remember, in general, C need not be a point where f is defined. It will be in this next two examples. So just to make it easy, remember that just like when proving convergence of certain sequences, you need to have a candidate for a limit. The same thing happens here. And these examples, these examples come from what are going to be defined as continuous functions. And so it just suffices to evaluate the function of the point. So this is example, first example. So consider f of x equals 2x plus 5. So we want to find linear function. And this is defining all of R. And so what is the limit? What is the limit of so find, I mean the thing I'm asking it this way because I mean this function will have a limit everywhere. So find as x approaches any point, this function will have a limit as it's defined everywhere and it's everywhere continuous. X approaches a given point C. So what do you think that this will be equal to? I'm sorry. So for the solution, again, the first thing to do is to find a candidate for the limit. So a candidate So to find the limit, we can simply evaluate the expression defines f at x equals c. Well, we suspect that to be the actual limit because this is not proof right now because we're trying to do everything rigorous. But just if you remember from Calc 1, these functions, the affine linear functions, polynomials, and many functions are continuous everywhere in their domain. And so for that reason, you would think that the limit will be given just simply plugging in C in the formula for f. This is correct. So the task will be showing rigorously that candidate is indeed the limit. Now the point that I want to make with this, the fact that you need to find a candidate, is that you have to make use of all the tools that you learned before. So for instance, when you were given expressions like x squared minus 1 or x minus 1, and you were asked to find the limit as x approaches 1, you were not actually asked to show that the limit was 2. But instead, what they asked you to do in Calc 1 was to find a candidate for the limit. You never actually show that this 2, the number 2 was actually the limit. But some algebraic manipulations allow you to find the candidate for the limit. So either you can evaluate things or use the rules you learned in Calc 1 to find a candidate for the limit. And this is what I wanted to stress, the fact that what you did in Calc 1 was not to prove that something was the limit, but to find candidates for the limit. But those candidates are actually they actually provide you with the right limit. That's sort of what we wanted to do back then, just to be able to get the right answer, even though we didn't actually show that the limits you found using these rules were actually the limits that you wanted to compute. We'll do that now. And so, and another thing I wanted to say is that sometimes if you're given a function that's defined in a piecewise fashion, make sure you use the right candidate for the limit. If you look at the limit from the right, see how the function is defined to the right, immediately to the right of the point in question. Because you may have different expressions for f depending on what interval you are in. Okay, so those are the only comments I wanted to make about this. Now, to continue now, so this way, so L should be equal to 2c plus 5. So we want to show that then that this is actually the limit. As I said, I mean, where does it come from? From plugging in c in this expression for f. So now, let's move this. So we want to show then that L equals to c plus 5 is the limit. Okay, so we have to use the definition as always. The definition, so using the epsilon deltas. Yeah, so it's worth mentioning also that in the book they also give an alternative definition using neighborhoods of points, but in practice, I mean, when you want to translate those conditions about neighborhoods, you always end up using the epsilon delta definition. So that's why I basically skipped that. It's not that important. It will not play any role in what comes. Okay, so now what do we want? So we said that the starting point is to give ourselves an epsilon greater than 0, an arbitrary epsilon. This is the definition of, I mean, this is what allows us to say that f converges to L as x approaches c, that for every epsilon, something happens. There's a delta greater than 0. So our task will be to find delta. Okay, so let epsilon be greater than 0, and let's write what f of x is. So we sit and we let, we actually don't let anything. So we compute. So let's simplify this expression. So we see that f of x minus 2c plus 5 is equal to, an absolute value, 2x plus 5 minus 2c minus 5. And we can cancel out the 5's, and we get 2x minus 2c, so we can factor a 2, and 2 comes out of the absolute value because it's positive, and well, it's absolute value of 2, which is the same as 2 times x minus c. So we want this to be less than epsilon, provided x minus c is less than delta. So this is going to be less than epsilon, provided x minus c is less than epsilon over 2. I'll just do the math. So if you want to impose such a condition, like this one, just isolate x minus c. This is what you are allowed to make small. X minus the distance between x and c. And so now you identified a candidate for delta. So given an epsilon, very small, you found a delta, which of course depends on epsilon, because for different epsilons, you will need to make sure that x is sufficiently close to c, so that depends on to guarantee that the image of f is close to the limit. So of course, if you want to be really close to the limit, then x has to be very close to c. So depending on how small epsilon is, delta may need to be chosen even smaller than, even smaller than epsilon. In this case, it's just a fraction of epsilon. But for the smaller the epsilon, the smaller the delta usually. And so we found a condition, we found a delta, and we've shown then that if for every epsilon greater than 0, we're able to find a delta such that if this distance is less than that delta, epsilon over 2, the distance between f of x and the supposed limit is less than epsilon. And this is how you proceed. So you write down the absolute value of fx minus the limit, and then you proceed in this way, making all cancellations. You may use some inequalities, and at the very end, you want to impose that so this is not something you know. Impose this at the very end. This ends up being less than epsilon. In order to make that make that quantity smaller than epsilon, you need to make some assumptions on the distance between x and the point C, which is distance between x minus c is one you want to make small, and what you're allowed to give yourself. It's a function of epsilon. That to prescribe how small you need to take x minus c in order to guarantee that this is less than epsilon in the end. So that was as far as this example. This is as far as this example goes. This is very elementary because this function is affine linear. So that's why you end up only with a fraction of epsilon. A more complicated example is an example where you actually have to take nonlinear. You consider the limit of a nonlinear function. So another example, let f of x be equal to x squared. What is the limit of f of x as x approaches some number c? Again, f of x is defined everywhere, and the function is a polynomial and it's continuous. You already know that. So a candidate is given by the value of f at c, so by c squared. Now we go a little bit faster because we already stop several points in the previous example, so hopefully we now understand what we have to do. So we let, this is the solution, if you will. We start by letting epsilon be an arbitrary small number. And as I said, we write f of x minus c squared, that's the limit. And we perform all the operations we need here in order to get something that will allow us to express everything in terms of the distance between x and c. So here this is the same as the absolute value of x plus c times the absolute value of x minus c. And, well, you know this is true because this is just x plus c times x minus c. And now, the first assumption we need to make. So this will be reminiscent to something we did before when we were analyzing the convergence or divergence of sequences. So this would be smaller than 2 the absolute value of c plus 1 times x minus c, provided that x minus c is less than 1. So we need that to be true in order to say that to bound this first part. Now the last part is smaller than epsilon, provided, again, now what did we do last time? Once we isolate the distance between x and c, we simply divide everything to obtain the condition on the distance between x and c. So this will be true as long as the distance between x and c is less than epsilon over 2 times the absolute value of c, 2 times the absolute value of c plus 1. So this is your delta. Okay, so last couple of things. So first of all, the delta depends, of course, on epsilon, but it also depends on the point, because for different points for different limit points in A, you may need to make delta smaller than for others. Whereas if the function is increasing, then for higher values, the function is changing more rapidly, so you need to make the neighborhood smaller. So the value of delta has to be made smaller for the same epsilon. For same values of epsilon, for different points, you may need to adjust the delta. And of course, it has to depend on the point. Here, the function x squared grows like this, right? So such, I mean, if you're here, the function doesn't change too much. So if you want this to be very close to the limit, you can take this interval here, right? While if when it's really, really large and it's changing very rapidly, just a tiny change in x produces a really big change in the value of the function. Right, so this interval here is smaller than this one, even though the neighborhoods here are the same. And the other thing here, how does this imply that, how does this condition that x minus c is less than 1 imply that this is less than 2, the absolute value of c plus 1? Well, this is just a triangle inequality, so x plus c is less than x minus c.